Hello and welcome to Engineering Design and Practice 1 first session. We will start with overviewing the CAD sessions we are going to be covering the first and second semester. So the session plan, you can see it on this slide. So in today's session, we are going to make an introduction to CAD, more specifically SolidWorks. We will discuss the basics of part modeling and 2D sketching. And in the following session, section 2, we are going to make progress to advance sketching and part modeling techniques. We'll talk about the design intent, and also how we can modify the parts. Session 3, we will cover the CAD assemblies, how we can create assemblies in CAD using the parts created. Then we will briefly discuss how we can produce photorealistic renderings of SolidWorks models, whether part of either part or assembly. And also we will make an introduction to the technical drawings. And in the last session of the first semester, we will be discussing drawings in CAD, how we can create engineering drawings in SolidWorks CAD software, and also how we can dimension and tolerance the drawings. And in the second semester, we will be covering the various CAE add-ins for SolidWorks. So the first semester is mainly focused on CAD, and the second semester is on CAE, so computer-aided design and computer-aided engineering. So we will be covering the FEA for stress analysis and thermal analysis over 2 sessions, and also we will be discussing dynamic motion analysis for rigid bodies, and also we will briefly cover CFD, computational fluid dynamics topic for fluid flow analysis. Here is the overview of the module assessment. So at the end of the first semester, you need to submit a CAD portfolio. So we will briefly talk about this shortly, and also a CAE report, which needs to be submitted at the end of the second semester. We will provide more details about this, and also the requirements and deadlines. So let's have a look at what you need to do for the first semester CAD assignment. So you need to create a portfolio of drawings and models. So in the first semester, as we said, we will cover the basics of CAD. So you'll get fundamental skills to create 3D parts and assemblies, and also engineering drawings. You can find some part drawings for a Stirling engine in your module handbook. So you need to reproduce all of those parts as 3D models, and you need to put them together to create an engine assembly. So using your CAD skills, you would also need to create drawings, a set of drawings for certain parts. So the overview of the requirements, basically you need to create the Stirling engine assembly in SolidWorks. you need to design your own flywheel according to the given criteria. So we are going to discuss the design rules of flywheels in coming sessions. So you need to create technical drawings of 5 key parts. So you don't have to reproduce all the drawings you already have in the module handbooks. So you just need to create the drawings of key parts, and also you need to correct the mistakes. So the drawings you would find in the module handbook, there are some deliberate errors or mistakes on the drawings. So you have to spot those mistakes and produce the correct drawings for your submission. As we said earlier, we will be doing the we will be covering the photorealistic rendering of so how to produce photorealistic render in SolidWorks. So you need to create an aesthetic rendering of your engine model, and you need to submit all these files in Moodle. So we are going to provide the details of the marking criteria and additional instructions how to submit your coursework. At the end of the second semester, you need to write a report on CAE, basically. So in second semester, we will cover various CAE add-ins in SolidWorks. So you can use these CAE add-ins to analyze your Stirling engine model. So in each session, we will look at different aspects to use CAE tools. So we will cover the stress analysis, motion analysis, fluid flow analysis, and thermal analysis. So you will write a report making some design suggestions using the results from the analysis you complete for your Stirling engine, and you need to justify your design suggestions with the data or results you would get from the simulations. Here is an example of a Stirling engine. So you can see the flywheel design. It's a very basic flywheel design. So there would be some requirements on how to design a flywheel. We will cover this. You can find more details about working principle of this type of engines on your module handbook. We can recommend some reading materials. The first one is actually a standard document from British Standards Library. It's called BS 8888. So it's available on Brooks online library. So if you would like to download this document, you just need to follow these instructions. So this is basically our ultimate guide for engineering drawing. So when we are creating an engineering drawing, we usually refer to this standard. There are also a couple of other books which, again, I can recommend to obtain those. The first one is called Mechanical Design. It's a very useful book which is available in library as a physical copy, or you can just download a electronic copy of it from the Brooks library. So if you just follow this link and make a search for mechanical design, you will see the book cover, and you can download the ebook. The other one is Shigley's Mechanical Engineering Design. This is again another very useful book where you can find some basic principles on mechanical design, how to make calculations, how to do some certain design decisions using engineering justifications. Again, I would strongly advise to obtain a copy of either of these books, and I'm sure that they will be really helpful throughout your degree and your career afterwards. Okay, so let's make an introduction to CAD. Before we start, I just want to remind you that I have also uploaded a SolidWorks installation video to Moodle. Please watch that video and make sure you have successfully installed SolidWorks 2020 to your local machine. Okay, so today's learning objectives. So we are going to make an introduction to SolidWorks. So hopefully by end of today's session, you'll have understanding about what SolidWorks is and what it is capable of. So we will discuss the different aspects that make up a complete model in SolidWorks. So we will discuss three main modes you can find in SolidWorks: part, assembly, and drawing. We'll be covering the basic user interface of SolidWorks, and also we'll discuss how you can organize a part. And also we will make an introduction to sketching. So this is the typically the first step you need to do when you are creating a part. So we'll discuss sketch constraints and how we can make a sketch fully defined and why we need to make that. We will discuss different sketch tools, so you can hopefully you'll be able to draw a basic and also more advanced 2D sketches in SolidWorks. We will also make an introduction to 3D solid modeling using various 2D sketches. We will discuss a simple 3D making features called extrude or revolve. And hopefully we will also be covering the complex sketches in SolidWorks, so how you can make your sketches more complex if it's required. Okay, here is an interesting quote. I think it's an old Chinese proverb. So it says, "Tell me and I'll forget, show me and I may remember, involve me and I will understand." So that basically means, from CAD learning perspective, you have to involve in hands-on activities when you're learning SolidWorks. So you can find numerous resources online, even on YouTube or any other blog post, where you can read about the CAD basics. You can watch videos about CAD, but if you don't involve in, basically you will struggle to build your basic CAD skills. So I would strongly advise you to obtain a copy of SolidWorks and then complete all the practices as we suggest in these sessions. Okay, so before we start talking about SolidWorks, let's discuss why we use CAD in engineering, or more specifically in mechanical engineering. So a simple definition or simple answer to this question is we use CAD because we would like to create, visualize, and evaluate 3D models of parts and assemblies. So that's the most fundamental reason why we use CAD. And obviously there are some other benefits of using CAD in engineering. It allows us to use various data input systems. That means we can store what's called metadata in our CAD models that includes critical information to make parts and assemblies. So that could be material information or any other geometrical information, or any other manufacturing instruction. Let's say if you'd like to apply any heat treatment or any other certain finish type. So you can also store those type of data in CAD systems. We can also analyze components and mechanisms. So these are more linked to the topics we will be covering in the second semester. So you can use CAD models to analyze components from structural, thermal, or fluid flow aspects. And also you can analyze mechanisms to get rigid body dynamics. This obviously would help you to communicate your design with others more easily. And also CAD enables us to create virtual prototypes. So we don't need to make physical prototypes, or even if we need to make physical prototypes, we need to make them at more matured state compared to how it used to done in the past. So we can virtually model 3D parts and assembly. We can check how they go together. We can make design decisions before physically creating prototype models. So we can take these design decisions in virtual environment. And finally, we can use CAD for CAM. It stands for Computer Aided Manufacturing. Again, we can use CAD models to program CNC machines using CAM tools. One thing to note here, although we create 3D parts and assemblies, and also all this information can be directly used for design communication, it is still far common to use 2D drawings, and all these drawings, so when we create those drawings, we need to we must always follow certain rules of drawings. So those rules are summarized in BSWW document I referred earlier, and also we will discuss some of them in last two sessions in first semester. But remember, the rules of drawing must always be followed. Okay, so what is SolidWorks then? So simply, it's a powerful 3D mechanical design software. So I'd like to emphasize this phrase, mechanical design. obviously, SolidWorks can be used for many other design purposes. I've seen examples, and you can easily find those, making simple online search. SolidWorks used for industrial design or product design or construction design or many other design point of view. But fundamental purpose of SolidWorks is mechanical design. Okay. So we can basically sketch ideas and experiment with different designs to create 3D models. So that feels that fits quite well to definition of CAD we made in the previous slide. So there are four main features, or let's say properties of SolidWorks. So we will discuss each one in details in coming slides. But to summarize, SolidWorks is basically a feature-based software. It's parametric, solid modeler, and fully associative. So let's discuss each of these terms to understand what they mean. So when we say feature-based, we can basically define that as so SolidWorks is basically makes parts using what we call features. So the features are building blocks of the parts. So we create features in what's this called feature manager design tree. So this is our design tree where we create sketches and features, and each feature is the building block of our parts. So let's take a look at this example here. So this simple bracket in the SolidWorks feature manager design tree, you can see there are 4 different features here. So the first 3 are boss extrude. So this is the very simple feature we use quite commonly in SolidWorks to create 3D boss shapes. And another one is called hole feature. So if we split this part to individual features, so this is pretty much what we would get. So we have a base feature here, as you see, and we have another boss at the end of this part, and then another cylindrical boss here. So you see that's the end boss is the second feature. The third boss is that cylindrical feature here, and the final feature is the hole in the center of this cylindrical feature. So these are the building blocks of a SolidWorks part, and we will use different features to create any geometry that we want to make in SolidWorks. We said it's parametric. So to understand what a parametric modeler is, first we need to understand what is non-parametric. So in non-parametric models, when you have an entity or input, let's say you have either 2D sketch or 3D geometry, so you can directly manipulate your geometry without worrying about the dimension parameters or any geometric relations which may or may not exist in your model. So let's take a look at this example. So here we have a rectangle in a non-parametric modeler. So we assigned a dimension to length of this rectangle. So if you'd like to drag and drop this end to increase the length or increase or decrease the length of this rectangle, in non-parametric modelers, we are free to do that. So we can just drag and drop, and if we initially had 50 millimeter or 50 unit, whatever the unit is, it could be imperial or metric unit. So we have a 50 unit dimension. So if you increase that to, if you drag this point and drop at, let's say, at 60, so this dimension would update to 60. So that means geometry drives the dimension. So whatever the geometry we drive, dimension will follow that. In parametric modeler, it works other way around. So we draw a geometry, in this case is a rectangle, and then we assign a length value to this entity, and if it's 50, and if you would like to change it to 40 or 60, let's say, we would like to modify, so we need to modify this value. We can just drag and drop the endpoint. So if you'd like to make this 60, we need to change the dimension value. Okay. Whereas in non-parametric, we can just manipulate the shape, and dimension is not going to control the geometry. So, summary, in a non-parametric modeler, geometry drives dimension. In a parametric modeler, dimension drives the geometry. We also said SolidWorks is a solid modeler. So basically, a solid model is the most complete type of model used in CAD systems, and it's an enclosed volume. So it's a volume, and it has its own mass properties. So in each volume and each part, each assembly, each 3D geometry, let's say, should have certain mass properties. So once we assign a material, that would define the density of the volume, and you can estimate the mass of your volume created. You can actually get the volume value in different units, and any other mass properties, we call them, such as surface area, center of mass, or different moments of inertia values, which can be obtained from SolidWorks. Something to note here, SolidWorks also has capability to produce surface models, which we are not going to be covering in this year at all. But we don't necessarily make only solid models in SolidWorks. We can also produce surface models, which are commonly used in industrial and product design. And also you can think of a car body example. So it has a certain sheet thickness, but that's typically made as a surface model, and then a thickness assigned to make it a volumetric or 3D solid model. But the most of the parts, or all the parts we are going to work with in this semester or in this entire year, are solid models, and they should all have certain solid mass properties. And finally, we said SolidWorks is fully associative. So that means the changes we made to the models are automatically reflected in the linked files or reference files. So let's elaborate what we mean with that definition. So let's take an example of this gray part here. So this part can be used in an assembly directly, and it may go together with another part, as you see here. So when we create this part and want to use this in assembly, so we don't have to reproduce this part in the assembly environment. So we just directly insert and use it. And similarly, when we are creating drawings, we can also use the actual part file to produce the drawing. Okay, and this drawing file and the part file will be linked. And similarly, we can make assembly drawings using the original assembly file. So we are going to discuss all these file types shortly. So the fundamental point here is when we make a change on, let's say, on this gray part, so we increase or decrease the diameter of this hole here, or we change the length or height of the part or the center cylindrical boss. So whenever we change this part and then we go to assembly, you would see that gray part is also updated as per the changes you made to the original part file. And similarly, your part drawings will also update the dimensions or views as linked to the original part file. And similarly, the assembly drawing views would also update to reflect the changes in the part file which you may have modified. Okay, so all the files that can be linked, and once you make a change on one, that change would be reflected on the reference drawings and assemblies. Okay, so now we can start talking about the different design environments that we can have in SolidWorks. The first and most basic element in SolidWorks Modeler is part. So the parts consist of primitive geometries and features, as we discussed in the previous slides. So we can put features to the parts, such as extrudes or revolves, lofts, sweeps, and many other feature types. So we're going to cover most of these features and more in this session and the coming sessions. As we said, the parts will be the building blocks for all of the models that you will create. So the parts will be used in assemblies and drawings. And typical part file in SolidWorks have an extension as .sldprt, SolidWorks part. Okay, so when you see a Windows file with this extension, it means it's a SolidWorks part file. Okay, so a part file is simply 3D representation of a single design component. The second component or second element is the assemblies. So they're basically a collection of parts which are assembled in a particular fashion using mates. Again, we will be covering assemblies in the third session, and we will discuss how to use mates to define the constraints and relationship between parts in assembly environment. And also, any complex models will usually consist of one or many assemblies, or we call them sub-assemblies. Okay, you can think of an example like a car assembly model would have many sub-assemblies and part. So one sub-assembly can be, let's say, engine sub-assembly, and in engine sub-assembly you can have different sub-assemblies and parts, and also in each sub-assembly you can also have different sub-assemblies and parts. So you can basically construct or build a tree of parts and sub-assemblies, and you will have a top-level assembly as your final product. Third and final element in SolidWorks is drawing. So it's a typical way of representing a 3D model which anyone can reproduce in any way, either physically or virtually. So if you have a 3D model, obviously you can show this to anyone, but 2D drawings are much practical way to represent the data or represent the design model and the geometry you create. So any engineer or manufacturer can recreate your part either in CAD to reproduce your 3D model, or in CAM or in manufacturing environment, let's say. So your 2D drawings should represent your 3D model clearly. Okay, so drawings are important because they provide a standard way of sharing your design. So we define certain standards, and in engineering there are certain standards to define rules of drawings. And as we said earlier, we will be covering British standard 8888 in this year, but there are many other standards. That might be an ISO standard or an American standard or any other national or international standard that you may think of. In SolidWorks, a typical file extension is SLD DRW. Let's also briefly talk about file referencing system in SolidWorks. So typically at top level in your reference tree, you would have a drawing file. Okay, so in that drawing file you can either have a part as a part drawing showing the dimensions and features of a part, or it can be an assembly drawing showing how different parts are going together or fit together. Okay, and each assembly may also have a part and subassembly or subassembly, let's say. Okay, so we can have either of these or both of those. So this is the simple structure we are going to be covering, but SolidWorks is capable of doing beyond that. So we can make parts from part. Let's say if you have a casting model and then you would like to define certain places where you would like to machine on your casting model, So you can originally create your casting model, and then you can insert your part to another part with different name or number that can be, and then add those machining details to a new part, keeping the casting model as your core. And there might be similar approaches for different design methods or design intents or manufacturing methods. Let's say typically an injection molded part may use split part. So when you're making a tool design for injection molding, you would like to split your part, and there are dedicated tools in SolidWorks for that. So we're not going to cover any of these in this year. Another example might be mirror part. So you can have left and right hand version of your design. So you just make one and just mirror your part to derive it from the original file. Okay, or you can have different library features. Let's say you can have certain hole size or o-ring groove size or any other machine element feature size that can be defined in library and maybe linked to a part file. Okay, and also you can link any other objects to a part file. So that could be a linked or embedded objects. That could be either a Word, Excel, or PowerPoint document, or PDF, or a VBA macro. Or you can have a design table to configure your part with different sizes. Okay, so we're not going to focus any of these. So finally, you can create multi-body parts, saving your assembly model as part. Okay, so your part doesn't necessarily have only a single solid body. You can have multiple solid bodies if you like to do that, and you can also extract your assembly to a part model in similar way. Okay, so our focus area, so we have a drawing, we said, which may either have a part, an assembly, and in assembly you can have parts or different sub-assemblies, and these three may grow as you like. Okay, but this is the very basic file referencing structure in SolidWorks, which you need to understand. Okay, so let's get started. When you open your SolidWorks, by default, you will have a blank screen and you will see the SolidWorks welcome screen on that. So when you go to File and New, you would see this dialog window here where you can select different different elements of SolidWorks. So as we discussed, either part, assembly, or drawing. Okay. Typically, we'll always start with a new part, and then we can make drawings and assemblies from a part. So when you create a new part document or new part file, you would basically enter the part environment. So on top of your screen, you would see this top ribbon. It's called dynamic toolbar, and in this dynamic toolbar you will see different tabs showing different design aspects or different SolidWorks tool sets. So this dynamic toolbar provides quick access to most relevant or frequently used commands. But if you can't find any of these the commands that you want to use, you can always go to insert, and a drop-down menu will appear. Then you can find any command available in path environment in SolidWorks under this menu. Okay, but majority of the paths we're going to make are only require use of features and sketch tabs. So in the features tab, you would see a number of commonly used features. So we will discuss most of these in this semester. And in the sketch tab, you would see you would see the button to start a sketch, a dimensioning button, and different sketch tools that may be used to create fundamental or any other complex sketch. On the left-hand side of your windows, you would see what's called Feature Manager Design Tree. So every time when you create a sketch or feature, a new entry on this tree would appear. So using the design tree, so you can make selections or filtering operations. So here you can make a search for certain feature names if you renamed your features, or different sketch names, or different elements you used, or different construction geometries if you used any in your model. So you can select features, sketches, drawing views, and construction geometries in the pane. So here, that's where you can make a selection of any of these elements. So design tree basically makes it easy to select items in model by name. That means when we create a feature or sketch, SolidWorks assigns a default sequential feature name that might be Boss Extrude 1, Boss Extrude 2, Boss Extrude 3, or Sketch 1, Sketch 2, Sketch 3, etc. So it would make sense to rename at least the features to make sense. So let's look at this example. So it's a model of nut. So here you can see the file name. So it's a nut, and then the modeler of this nut renamed the features. So the first boss feature is called head, and there is another feature called flange, head trim, and through hole. So imagine when you have a complex part, you will have a growing list of features, and it would be easy to find whichever the feature you are looking if you have renamed them correctly. Okay. So you can display the dimension of a feature by double-clicking the feature's name. You can rename it just slowly clicking 2 times on the name and enter a new name. What else you can do is to suppress or unsuppress features, or if you are in an assembly, you can suppress or unsuppress assembly components. You can view the parent and child relations by right-clicking a feature and selecting parent and child. So what that means, so when you are making a feature, if that feature is somewhat linked to a previous feature created on top of this tree, so it would have a parent-child. These two features would have a parent-child feature relations. So we will discuss how this parent-child relation mechanism works in more details. Okay. You can also use the feature tree to locate errors and warnings with the model. Let's say if you delete one of these features, let's say you deleted the flange, and if there is a parent-child relation between the flange or, let's say, the head trim feature, so once you delete the flange feature, you would see some errors will appear, the child feature. So you can spot this error in the design tree and correct them. You can also change the order of features, so you can just drag and drop the features in the tree to reorder them. So this changed the order in which features are regenerated when the model is rebuilt. So every time you make a change on this design order or you reorder the features, you need to rebuild the model. Again, we'll show that have to rebuild a model when it comes to that. Okay. If you don't do that, this can lead to errors. So it's good practice to plan a part properly first. Again, we will talk about how you can plan your part, what would be the fundamental points or fundamental aspects you need to look when you are planning a part. Design tree also provides the following folders and tools. So you can use the rollback to temporarily roll the model back to an earlier state. Again, you will see how to use rollback in the hands-on videos. So this rollback option or this rollback tool is going to help us to fix the errors. So we will see how to use this. The main view window shows the part assembly or drawing you are currently working on. It shows the graphical representation of the file you are working, whether it's a part or assembly or drawing. You can change your view of part by holding middle mouse button to rotate the view. So you can hold the middle mouse button and keep holding it to rotate the view. So that's one way of manipulating your model view. If you are holding the middle mouse button while holding the control key on your keyboard, you can pan the view. So you can scroll the mouse wheel to zoom in and out, holding right mouse button when selecting a view. So you can explore various view manipulation controls on SolidWorks. And additionally, on top of your main view, you would see this heads up menu where you can see different view options. You can explore each of these. There are many commands or buttons here. The first one, it brings your model fit into your screen. So if you have zoomed in and zoomed out too much, you can press on this button and that would fit the model to your screen. Or you can use F key as a shortcut to this button. The second one is to zoom to a selected area, so you can use box selection to zoom into a certain area of focus. The next one is to bring to the previous view. So if you have changed your view and you want to move back to previous view orientation, you can use this button. And the next one is for section view. We're gonna discuss how to use that. So another one is to show the main view of your model. So you can select top, right, bottom, left, front, rear type of main view or isometric views of your model. The next one showing the view style. So please try to explore all of these options to find out and understand how they are functioning. So we talked about the F key. It used for bringing your model to fit your screen. The other useful shortcut which you would occasionally need to use is Control 8. So that brings the selected plane or face to normal to your screen. And there are also a list of shortcuts which might be useful during the first semester, particularly, or it's good practice to using some shortcuts to practically run some commands on SolidWorks, typically open and saving operations, or these are default or standard Windows shortcuts. You can use Control C or to copy any element, or Control V to paste. There are some specific symbols that you would need to insert, especially when you are doing your drawings. If you hold the Alt key and input this code, Windows will insert either degree, diameter, or micro symbol regarding the code based on the code you input. There are also some user interface shortcut. Control Q is rebuilding the part we said earlier. Occasionally you would need to rebuild your components when you make certain changes in your sketch or in your features. That's typically a very useful command when you are editing a part, assembly, or drawing. Control tab moves among open documents. So if you have more than one part, assembly, drawing open, so you can use Control tab shortcut to switch between those documents. Enter key repeats the last comment. Let's say you created a feature and you want to create similar feature or same feature, so you don't have to navigate to that feature button on the dynamic toolbar. You can just press enter button to repeat that command. Okay, some useful selection shortcuts. Again, they are standard Windows shortcuts mostly, but holding the control key. So if you do holding the control key and left click on your mouse, that would select multiple entities. And similarly, if you hold Shift and make a selection through a transparent face, you can select the transparent face itself. Otherwise, SolidWorks will disregard that and select the next opaque face appears on the screen. And finally, Shift and left click, that basically selects multiple items on the feature manager design tree. Please try to use this shortcut to speed up your modeling. I hope you can explore many more useful keyboard shortcuts, but those are most required ones for your assignment and any other tutorials we will do together. First thing we want to do is set the units. No matter which CAD software you are working on, it's good practice to check your unit system first and ensure that you are working with the right unit system that you want to work. So there are a few ways to check that. You can either go to documents and sorry, you can either right click on the part name and then go to document properties. Then you would see the option windows will pop up, and you can go to unit system, and here there are a few standard unit system, or you can make a custom one. So the units we will be working is millimeter, gram, second units. In mechanical engineering, we mostly work in these units, but in civil engineering, meter, kilogram, and seconds may be more preferred, or any other practice can be used, similar to using imperial unit system, or if you would like to define any other type of custom unit system, you can just select the custom tab and edit the units. But if you select the millimeter, gram, and second, that should be fine for our applications. Okay, let's make a start with SolidWorks sketching. So nearly every part we produce in SolidWorks starts with a 2D sketch. So it's important to understand how sketching works and why we need that. So from a sketch, you can create features which would be your 3D geometry. And as we said earlier, there are different fundamental feature types in SolidWorks. So let's start with a simple I-beam profile, as you see here. Okay, so using different features, we can create different geometry types. So extrude feature is basically applied to a single direction, and you extrude your sketch or 2D profile to 3D dimension. You can think that is a stack of these profile along a certain length. So that's a very simple operation. You draw the sketch you want to extrude and select the extrude command, and this adds the third dimension to your sketch. Okay, it's basically a thickness or length that you can add to your sketch. The second feature type is revolve. So with revolve, you can rotate your sketch around an axis, either a full rotation 360 or to a specified angle. So that would create a wheel-like or revolved geometries. For sweep, so you would need two different sketches. The one sketch is your profile, the other one is your path. And your profile basically follows the path, and it creates the geometry. So you can see an example in this model. And the final type is loft. So the loft feature blends two different profiles. So in this example, we have an I-beam shaped profile and then a round profile at certain distance from the from the first profile plane. Then we blend these two profiles to construct a geometry. So these are add-in geometry, and in SolidWorks they're typically called boss features. So you can hear boss extrude, boss revolve boss, swept boss, or loft boss type of feature names. And all these features also have similar cut operations. So you can cut extrude your sketch profile, or cut revolve your sketch around an axis, or swept cut your profile along a path, or loft and cut loft your to profile to remove this this shape from a larger geometry. So we will make example each of these feature types with the cut counterparts. Let's start with making a part. So we said that SolidWorks parts are made of features. So the most common feature type we would use is extruded boss base. So as we discussed in the previous slide, we would need the base sketch and then an extrude command to add the third dimension to this sketch. And similar to this example, so we can have a circular sketch with 100mm diameter and extrude this up to 75mm height to create a cylinder. The other type could be cut extrude. So this is to cut and remove material from a base geometry with extrusion. There are many ways to extrude a surface. If we think of this simple geometry, we can either draw this front rectangle and extrude it to third dimension, which would be normal to this this screen plane, or we can create a rectangle to show the top face or the bottom face, and we can extrude it up or down. And the third option, you could extrude this rectangle, the side face, extrude it to create the third dimension as length of this beam type of geometry. So 3 ways to make this component. So which one is best? They're all the same. We just need to plan ahead which one is the best, and that planning is our design intent, which we will discuss shortly. Okay, so when you start a part or assembly in SolidWorks, it usually comes with 3 main planes and an intersection point of those 3 planes. So we have front plane, and you can see that it is XY plane. We have top plane here. So in the part coordinate system, that would be XZ plane, and right plane, which would be YZ plane. And intersection of those points is origin. So the first thing we need to do is to start a sketch, and we always need to select a plane or face to start a sketch. You can only select a face of a part if you have an existing geometry in your part, but when you start a new part, you need to select one of the main planes we discussed in the previous slide and go to Sketch tab and select the first command, which opens a sketch in your model. So once you are in sketching mode, you can start using different sketch tools. And typically, we generally start with either line, circle, or rectangle type of sketch entities. So these are the most fundamental shapes we start. Okay, here is the first task that you need to complete. you can start off a new path in SolidWorks and create a new sketch and try to explore all these sketch options. You would see different drop down next to the each sketch command, and in the drop down you would see different ways of making the same geometry. Let's give an example. For a circle, you can make a circle in a few different ways. The first method is to select the circle origin and then draw a circle and select a point on the circle itself. So that would construct the geometry. The second method is called 3-point or perimeter circle. So you can click on 3-point on your sketch and SolidWorks would create a circle crossing those 3-point selections. And there are also a few other line types or different rectangle methods or different arc types. So what I would like you to do is to explore these sketch tools that are in these 3 red boxes. So try to add different basic shapes, arc, rectangle, or line. See what a point is and try to add some center lines, and we're going to discuss what a center line is later. And also try to add some sketch fillet and sketch chamfers. And after that, start a new part and try to create a simple cube. And on a new part, try to create a simple cylinder. And also try to find the 3 ways of making a washer. So you need to explore some of the features here. You can use extrude features or revolve features or cut features if you'd like. And also try to find the best way to add a chamfer. Okay, after exploring different sketch tools, now we can talk about defining a sketch in SolidWorks. This is probably the most important fundamental point in SolidWorks, and you need to understand how this concept works. Okay, so if you have explored the sketch options and you've tried to create different sketch geometries, you might have noticed that when you create a sketch, all the lines typically appear in blue. So when you see a blue line in your sketch, that usually means your sketch is underdefined. So the definition of underdefined sketch is that your sketch has not been constrained properly. That means there isn't sufficient information to fully define your sketch. So you are free to manipulate any of these lines if we look at this example. So their position with respect to origin is not defined. Their length or orientation are not defined. So we use 2 main tools in SolidWorks to define the sketches. We use dimensions to define the size of the features, and we use sketch relations to define orientation and any other relations regarding to the feature sketch entity. Okay, so let's have a look at this example here. So as you can see, all the lines are now black. That means any black line you see is fully defined, and if you see no blue line in your sketch, that means it's completely defined sketch. So you can add relations and dimensions to define each sketch entity. Okay, so the first thing and the most essential thing that you would need to do is to define your sketch position with respect to origin. Okay, so you see that little blue graphic here. So that defines the relationship between this edge of the geometry and the origin, and it is a coincident relation. So we're going to discuss different type of relations shortly, but that's the first point to start with. And it is also very good practice to always start your sketch from the origin. Okay, so that's the most important thing which you need to practice and implement to your modeling method. So you should always start from the origin and draw your lines or arc or circle or any other sketch element you're using from origin. Okay, so once you have started your line, let's say, so let's start with this horizontal line. So we can draw a horizontal line, but we should also tell software that it's horizontal. Again, we use sketch relation, and you see this blue graphic here that defines a horizontal line. If you don't see that, although it is on horizontal alignment, software would never know that and would never constrain it to run horizontally. So you can make it with a slight angle, or you can completely rotate it to be vertical. Okay, so using many sketch relations, we can define the lines being horizontal or are coincident, or there are a few other methods to define the sketch relations. So once you have added all the required sketch relations, the second tool we use is dimensions. So we input the dimensions, and remember that we said SolidWorks is parametric modeler, and these parameters are dimensions and sketch relations. So this is the most fundamental part of SolidWorks. You have to remember it's a parametric modeler, and you need sketch constraints or sketch relations and dimensions to fully define the sketch. So again, let's have a look at this example. It's a horizontal line starting from the origin, going 25 millimeter, and then a vertical line starts and it goes up to a point 35 millimeter from this horizontal line, and then we have another horizontal line at top, then an angled line with 40-degree angle is drawn, and then another horizontal line, another vertical line with 15 millimeter length is drawn. So all these sketch relations and dimensions are fully defined in the sketch. Once we have fully defined the sketch and we would like to add more relations or dimensions, effectively we are over defining a sketch. So fully defined sketch, it contains the required amount of information to fully construct and define the geometry. Once you add anything else to a fully defined sketch, that would be overdefined, and SolidWorks would show overdefined geometries in yellow. And if you have any other error geometry or any other incorrect geometry, let's say, it would appear red. So every time you must ensure that your sketch is fully defined and all black. Let's talk about the sketch constraints. So we said we first need to apply the sketch constraints to any sketch we draw, and then we would apply dimensions. So once you have made a selection on any line or any point, on the left hand side of your SolidWorks window, you would see different sketch relations that you may apply. So let's have a look at this example. If you hold Control and select these two lines, you can make these collinear. That means they're on the same line. And also you can make them equal. You can make two lines parallel or two lines perpendicular. You can either define vertical or horizontal lines, so that would be with respect to origin and sketch coordinate alignment, as you see here. So we have a horizontal axis and vertical axis. So when you draw a vertical line, SolidWorks would automatically include the vertical relation to that line, but if it doesn't, you should do that. Otherwise, although it would appear as vertical, it wouldn't be defined as vertical. Okay, or you can define the tangent relation between an arc and line. You can make two arc or circle coincident, or if you would like to make two arc or circle in the same radius or diameter, there are co-radial option, and there are a few other sketch relation that you can use, such as symmetry. The one thing that almost solves all the underdefined sketch issues is fix. Basically, what fix relation does is arbitrarily fix the sketch in the position as we draw and in the length as we draw, but it doesn't define any relationship. Okay, so once you fixed a sketch, it would appear black as fully defined, but that's not going to define any relationship between the entities. Okay, therefore you should avoid using fixed relation at all. Okay, you should never use this, and you should always use the other sketch relations in your sketches. And when you are making your assignment, if you use fix to arbitrarily fix your sketch entities and fully define your sketch, we can easily spot that, and you will lose marks for doing this. Okay, please avoid the fixed relation at all. And if SolidWorks added a relation that you actually don't want to do, you can simply select the graphic of that sketch constraint or sketch relation, then delete it from the delete on the keyboard. Okay. And once you have defined all the sketch relations that you need, the next step is to dimension your 2D sketch. Okay, so to do that, we use a tool called Smart Dimension. So dimension types are determined by sketch entities you select. Let's have a look at this example. So when you select the Smart Dimension and click on this line, you can, as you see, this line is somewhat an inclined line, so it's not horizontal or vertical. With Smart Dimension tool, you can either define the horizontal distance between two endpoints of this line, or horizontal distance between the two endpoints, or the straight distance between two endpoints, which would be the actual length of the line. Okay, so the Smart Dimension tool allows you to dimension your sketch entities in many different ways. You can also use Smart Dimension to add dimensions between 2 points or a line itself, or you can add angular dimensions, or you can add circular dimensions. Okay, so it depends on the sketch entity that you select after Smart Dimension. Okay, here is another task that you need to complete. All I want you to do, start a new part and open a sketch on any plane that you want. It could be front, top, or right. That's entirely up to you. And start drawing this sketch with given dimension. Okay. One point that I want you to be aware of and pay attention to is when you are given a sketch similar to this, always try to repeat the dimensions as it appears. So what do I mean with that? Let's have a look at the top bit of this part. So we can easily draw that shape, this outline, and we can add a smart dimension between this line, this vertical line on the left, and the vertical line on the right, and add a dimension value of 90 plus 21. But in this sketch, it's not actually dimensioned in this way. Again, this is called design intent, and we haven't talked about this yet. We will talk it shortly, but at this stage, all I want you to do, just add the dimensions as you see on the screen. Okay, and once you finish this sketch, you can extrude it to a certain thickness, and I want you to find out whether this part is over or underdefined, and if it's overdefined or underdefined, how it can be fixed, or if the sketch is fully defined. The other task that we will be doing today is another sketching example. Again, I want you to start a new part and create these three sketches as you see on the slide. You can add them to the same sketch, so you don't have to separately create sketch or part. That they can all be in the same sketch, but try to dimension them as you see on the screen. Okay, so you have a rectangle with 100 millimeter length and two holes positioned 25 millimeter from each end of the rectangle. And in this example, we have the same rectangle, but at this times hole positions are given from one end of the part. And the other example is the same rectangle, but at this time the distance between two hole center is given, and we also have a center line on the rectangle. So try to create these three sketches, extrude them to 10 millimeter, and go back to your sketch and edit your sketch. Just adjust the dimension, some of these dimension, particularly the length, adjust the length on each rectangle, and see how your sketch changes. And also try to find out if your sketch is fully defined, and if it's not, what information that you need to make it fully defined, or you need to remove from the sketch if it's over defined, and you need to remove from the sketch to make it fully defined. Okay, and also you can look at where to add your origin, so where your part origin can be located. Okay, so from the previous task, making the same geometry but with many different ways showed us why design intent is so important concept. So let's have a look at what design intent is. So it's basically how a model behaves when dimensions are modified. It's a very simple definition, and if you consider the example we just made, you can understand that you can see how the model behaves differently with different dimension and methods. Okay, so this is our design intent. An example of design intent is how you create and dimension a hole in a block. So the hole can be a certain distance from a corner or edge, a certain distance from the center, aligned to the middle of a face. Okay, so this is the task that we just completed. If the size of the block or the hole changes, the part rebuilds correctly if the design intent has been considered in the definition. So you should understand how you can edit or modify your design in the future. So you have to capture the design intent at design stage. Okay, so if you have a hole, if you have two holes on a block, then you need to understand what's the critical dimension on your model, whether you want to distance the holes from the corner, or you want to control the distance between two holes, or you want to control the position of your holes from a certain edge. So this is the design intent. Here is a good example of design intent. Let's have a look at this image here. So we have a hinge mechanism here with two main parts and a pin connecting these two parts together. Okay, so if we change the length of these parts or this hinge, the holes may change in a few different ways. Okay, so let's think of the example we just did, and you would see how these holes could have changed. So if we had dimensioned the holes from, let's say, this bottom edge, so from this edge, all holes would remain in the same place. But if we have captured the design intent, which is in this case to space the holes more evenly along the length, and when you modify the length, it would just behave as intended. So why design intent is important? Effectively, it's minimized rework. So you should tell your CAD package, whether it's SolidWorks or any other CAD package you can use, you should tell your CAD package what your intent is. Okay, to do that, you must plan ahead. Okay, so you should make your plan before making any sketch or any part. And your plan should capture your design intent in the model. Okay. Sketches should be fully constrained, so they should be fully defined in SolidWorks terminology. In more generic terms, fully constrained. And you want to avoid all undesired changes in that way. Okay, so if you have anything underdefined and you make a change in one dimension of your model, then any underdefined sketch entities would not behave would not behave as intended. So you have to rework all of those. Okay. You should also name all features in your tree to make it easier to modify. Okay, so that may not be directly linked to your design intent. It's just a good practice in SolidWorks. If you rename your features, then it would be easier to go back in the feature and modify them and find them in your design tree. Okay. SolidWorks modeling is 90% design intent and 10% of 10% knowing the program that you are using. So we'll try to teach you the program, which is SolidWorks we will be using, but to develop good design intent practices, you should make you should make lots of modeling practices and complete all the tutorials. Think about how you can model a part in SolidWorks when you see anything in your life. So here is another design intent task. At this time, I want you to make this part in 3 different ways. If you can't make it, don't worry about it. We will show how you can use these 3 techniques. But let's have a look at and try to determine how to create this part using 3 different design intent. So the first one would be multiple extrudes. The second one would be revolved sketch. And the third one would be manufacturing approach. I want you to take some time and think about all of these three design intents and try to model them in SolidWorks. The dimensions are not important. You can use any diameters to make it look alike as in this image. So the whole purpose is to explore different design intent options for the same geometry. Okay, so we have a few different practice tasks. So when you get chance, please try to complete these models in SolidWorks. So normally each one shouldn't take any longer than 10 minutes to complete, and you can assume each grid is 10 millimeter. So if you look at this model, so we have 1, 2, 3, 4, 5 unit length. So each one is 10 millimeter, so that would be 50 millimeter width and 10 millimeter height and 20 millimeter depth. Okay, so you can use this approach, try to make these parts with different design intent techniques. So there would be a few other examples that I want you to complete. Let's move to the next slide. Okay, here are a few similar parts. So this F arrow means the front plane. So you can see, so this is the front view angle. So you can select your front plane accordingly. And the last 2 examples are on this slide. So please try to complete those 6 simple part models in SolidWorks to understand the design intent and how you can make them differently. Okay, so if you have completed all these exercises, then you would have some basic understanding about SolidWorks sketching. So far we've only made simple sketches, simple lines, simple arcs, or simple circles, a fairly simple sketches. And it's actually good practice to keep sketches as simple as possible so that you can go back to your model in the future and modify your sketches easily. So it's good practice to have one sketch per feature. So keep your sketches as simple as possible. Imagine the example we did in the previous task. You have a rectangular block with a hole in the center. You can either have a rectangle and a circle in your sketch and just make an extrusion as one step, or you can split these 2 elements to individual sketches and use 2 different features. So first you can extrude the block and then you can cut extrude the hole. So this is more preferred approach, and in the future it's easier to modify if you want to modify your part. However, sometimes we would need to make complex sketches, and making simple sketches is not possible. So in that case, we need to be able to draw complex sketches. And typically, we have a number of tools that we use when we make complex sketches. The first one is construction geometry. So this is the dash dot type line on your SolidWorks sketching tools. It just helps us to construct or build actual sketch entities on our model, but it doesn't create any feature, shape, or any geometry in our 3D model. Okay, the other way is patterning the features. We can use a few different ways. 2 main one is linear and circular pattern. We'll discuss them in details. Okay, and also we can use mirroring. So we can just mirror a sketch with respect to a construction line. And the final 2 elements that you need for complex sketches are you are familiar with, dimensioning and sketch constraints. So let's take this part as an example. Have a look at a few points that we would like to discuss here. Before we make a start and think about the actual geometry itself, let's have a look at a few terms that we see here. Okay, so when you see this symbol, it shows the diameter of a feature. So it's showing that center boss diameter is 16 millimeter. So all the units are millimeter, by the way, unless otherwise specified. Okay, and R means radius, so it's showing the radius of this feature. And M10 is showing a thread size, so it shows in that hole here. So how do I know it's a hole? Looking at this section view. So section view is cutting the part from this line, and we have a hole or cavity here. So that hole has metric 10 thread with 14 millimeter depth. a few other points. So we have a side hall here. It goes all the way through to the part end. Again, this is showing the design intent. We'll discuss the end conditions in SolidWorks features, and you can define different end conditions, one of which is through hole. Okay, and it's showing the angle of this center boss is tapered to 10 degree. Okay, and we also have a drawing note here. The general wall thickness is 4 millimeter. So where it's not specified, the thickness is 4 millimeter. So as you see here, that thickness is 4 millimeter, and that thickness is also here 4 millimeter, and that thickness is again 4 millimeter. And all unspecified fillet radii is R2, so radius 2 millimeter. So wherever we see any unspecified radius, that would be 2. Okay, so let's have a look at the basic outline of this geometry. So the basic shape is somewhat unorthodox. So we see that we would need to draw this complex sketch if we would like to extrude this up to a third dimension. Okay, but looking at that, we see it has only 3 main dimensions. Okay, it's showing this 60 millimeter diameter and radius 6 and radius 8 on 60 millimeter PCD. So PCD stands for pitch circle diameter. That means the center of this 8 millimeter radius is going to be somewhere here. It's located on a pitch circle with diameter of 60 millimeter. So you can imagine a circle with 60 diameter from the center, and the center point of the radius would be on that 60 millimeter diameter circle. That what pitch circle diameter is. And interestingly, the outer diameter of the part is 60 millimeter. Okay, so these two could have different values. It's just coincident that they have the same value. Okay. The other dimension is that edge blend is 6 millimeter. So let's have a think about this part and see what else can we determine about the shape. So if we look at this shape, it's actually repeating itself with certain pattern. So let's take the 1/6 of this part. So the 1/6 of this part, which is a 60-degree segment of the part, just repeat itself 6 times to create the outline of this geometry. So if we somehow draw this 1/6 segment of the outline and using the circular pattern tool to repeat that geometry 6 times about the center point, we would complete the outline shape. And if we look at the outline shape in isolation, so let's have a look at, let's assume that there is also another central line going through the center of this segment. That segment is actually symmetric about this line. Okay, so we need to capture this somehow. Okay, so what we have a series of arc which is mirrored about a line, and then we have a segment which is repeated six times to complete the full geometry. Okay, so to capture all these, we start with a number of construction geometries. Okay, so let's draw a circle and let's draw a circle from the origin and a vertical line, and select these two lines and set them to construction line. So the next step is to draw the mirror line of the 1/6 pattern as we just discussed. Okay, so it is just this line here. So we said the repeating shape is 1/6, so therefore 60 degree of the part, and we are drawing the midline of this segment, which would be at 30 degree. Okay, so we have just another construction line at 30 degree. So to add a degree or angular dimension, so you need to select the smart dimension and select two lines, then you can add an angular dimension. Okay, so far we have only drawn construction lines, and now we will start drawing the actual outline shape. Okay, so we see here three circular dimension. So if you look at this 1/6 segment, we see three arcs in series which are tangent to each other. So we will start with an arc from the intersection point of the circular construction line and the vertical line, and then draw an arc segment. Then we continue with tangent line to draw the second arc, and carry on doing the tangent arc to draw the third arc segment in the series. And once we've done that, we will add dimensions. Just make sure you add the dimensions correctly. If you define the center point of this arc at the intersection point of the vertical line and the circle, so that circle would act as your PCD. Okay, so that's the 60mm circle, which is your pitch circle, and then this 8mm radius is on the PCD. Okay, so we just draw in this bit here, and then we have 6mm radius with tangent continuity. We just add 60mm radius to the second arc, and the third arc is going to be at 60mm radius and concentric with the pitch circle diameter. Or we can just select the last arc or the third arc in the chain, and the PCD or pitch circle, and add a corradial dimension between these two. Okay. As next step, what we want to do is to copy and mirror this arc chain about the line angled at 30 degree. So we have to select these three lines. If you just right click on one and go to select chain, you would see that all these three lines would be highlighted. Then you can go to mirror tool on your sketch toolbar, and then you need to select this angled construction line in the mirror about selection box. And once you have mirrored this geometry, you can click OK to come out from the mirror tool. And next step is to pattern this geometry about the center point. So to do that, you still need to select all these points, but at this time we will use circular pattern tool. Okay, you can use the same method, just right click on an arc and select the chain, and at this time from the linear sketch pattern drop down, select the circular sketch pattern. Okay, so you would see that entities to pattern, so these are the lines you are patterning. You'll see a list of arcs here. Just make sure you've selected all the arcs, and then by default the mirror point would be the center point of your model. If it's not, just make sure you select center point, and you need to set the number of instances to 6. Once you do that and click OK, what you would see is a complete outline of your part. So that 6 here indicates the number of instances in your pattern, and you have mirrored your part, so you can see a lot of mirror sketch relations in your copied geometry. Okay, so here is your end result, and now you can extrude your sketch to third dimension. If you have completed this example in your own, you can see some issues when you are extruded to third dimension, and this is an inconsistency in your sketch when we use pattern tool, and you will see that SolidWorks would apply a thin feature properties to your sketch. That means SolidWorks doesn't view this sketch as a fully closed sketch. Okay, it thinks it's still open sketch, and it tries to create a thin feature. So at this stage, you need to cancel the extrusion operation and go back to sketch tool and find the repair sketch. So once you click that, SolidWorks would bring up this dialog box showing no problems on your sketch, and now you can try to extrude again. At this time, it should extrude it as solid block. Okay, using the methods we discussed today, you can complete these parts. I believe you have all the skills to complete this part. So please try to complete it in your own time and save this part, because we are going to use this part again in the future sessions. Okay. So the previous sketch didn't work because it was essentially overdefined. What we did basically, we drew one half of the segment at 30 degree. Okay, we mirrored that to 60 degree, and we repeated the segment 6 times to 360 degree, which we are also imposing since this is a complete circle. Okay, so that's the reason why we overdefined that. So we have imposed a complete circle in the model, and we have also dimensioned that 360 using a circular pattern. Okay, it's just repeating the same thing or telling the software to do the same thing twice in the sketch. So that's a definition of defined sketch. A better approach is to simply remove material and apply this is as a feature pattern. Okay, so we said in the previous slides that we should always want to keep the sketch as simple as possible, and we want to use more features and less complex sketches. So following this rule, you can try to recreate this. So you can simply draw a circle with 60mm diameter, and then you can cut extrude the 8mm radius on 60mm PCD cutouts, and then apply 6mm radius to the corners of the cuts. And here we have a number of practice parts. Please try to complete all these parts in your own time before the second session, and we would need to use these parts in coming session, especially when we are making assembly. You'll need to bring all of these parts to your assembly model. Okay, so we have a number of parts. So we have a washer, we have a control rod, a control screw, a valve, and that's all. So please complete all these parts and save and store them. So before completing the video and this session, there are a number of my SolidWorks videos I would recommend you to watch. So these are all related to the topics we have covered today, but hopefully you will help you to understand the concepts in a better way. Okay, so please just watch these videos in order. So there are some sketching at basic level, so how to start the sketching on a sketch plane or face, how to use entities like lines or central lines, how to use rectangles, circle, arcs, how to use smart dimensions, how to add sketch relations, automatic relations, fully define a sketch, and more complex sketch shapes like ellipse or slots. And once you watch these basic sketching videos, you can go to basic part modeling videos about extruded bolts and extruded cut, about revolves, about editing parts, and fillets and chamfers. And finally, there are some advanced sketching videos showing how you can edit sketches, how to use sketch contours, and how to use sketch fillets and chamfers. So these are very important and basic concepts that you need to be familiar to understand the topics in the second sessions. Okay, so please spare your time to watch these videos and understand the concepts. And finally, if you would like to learn more about and if you need to make more practice, in the Welcome SolidWorks window, we say there are a few tabs. You can go to Learn tab and Tutorials, and if you click on the tutorials, you would see step-by-step interactive instructions, and I would recommend you to complete a few tutorials here. So once you click on the tutorials, you will see the SolidWorks tutorial windows would appear, and from the Getting Started tab, you can complete Introduction to SolidWorks and Lesson 1 parts tutorials in your own time. Okay, so I believe we have covered all the learning objectives as we defined at the beginning of the session. We've covered the SolidWorks basics and capabilities of SolidWorks. We looked at the different SolidWorks elements that we may use, such as parts, assemblies, and drawings. We have discussed the SolidWorks interface and how a part is organized in SolidWorks. We discussed sketch constraints and dimensions and why we need to fully define sketches. I hope you all now able to draw simple 2D sketches as well as some complex ones, and you can create simple solid models using various commands like extrude and revolve. So now you all have skills to make some Stirling engine parts that you can find in your module handbook. All the parts are listed here. You have skills to make. Please start making those parts as soon as you have opportunity to do, and you will have time to rework all these parts in the future if required. I hope you enjoyed this session. I'm looking forward to seeing you all in the second session. Thank you very much. Bye bye.